All right, carrying on where we left off, we're talking about the energies of electrons in different orbits around the nuclei of atoms. And I just wanted to reiterate that since nature in general prefers things to be as stable as possible, and in nature, stability generally means low energy. In fact, it makes sense when you think about it. I mean, if you even think about yourself, imagine that you've just eaten a whole lot of sugar and drank a couple of Cokes. You're going to be bouncing off the walls. You're going to be in a high energy state, which is unstable. And then when you crash from all that sugar, you're going to be in a very low energy state, and all you're going to want to do is lie on the couch and watch TV, and that's very stable. And that's the way things are generally in nature. High energy is unstable, low energy is stable. Nature prefers things to be stable, in other words, as low as possible in energy. And because of that, you normally find atoms in what are known as what's known as the ground state. And the ground state is just basically a condition where all of the electrons in the atom are in the lowest energy positions available. And in a hydrogen, which only has one electron, that means that that one electron should be in the first orbit closest to the nucleus, because that would be the lowest energy position for the electron to be in. And that will be the ground state for hydrogen. Now, in order to get that electron to go anywhere else within the hydrogen atom, you're going to have to add energy to that hydrogen atom, and that will result in what's known as an excited state. Excited state results from absorption of energy, and that causes one or more electrons to jump from where they were to an orbit of higher energy farther away from the nucleus. And that's, again, called an excited state. That's unstable and it won't last for very long. But when that happens, that means that there will be a vacancy left behind where that electron used to be. And the energy absorbed will be equal to the energy difference between the original position of the electron and its new position. So not only are atoms capable of only emitting certain energies of electromagnetic radiation, they're only capable of absorbing certain energies of electromagnetic radiation. If you add just the right amount of energy to promote an electron in hydrogen from n equals 1 to n equals 2, then the atom will absorb that amount of energy and the electron will end up in n equals 2. If you add only half as much energy as you need to get the electron from n equals 1 to n equals 2, the electron will not go to n equals 1 because you didn't add enough energy. It'll stay right where it is. And in fact, the atom will not absorb that energy. It'll just let it pass right through because it's not enough for it to do anything with. And so they can only absorb, and atoms can only absorb, and they can only emit certain energies. Excited states, as I said, are unstable because they're not the lowest possible energy. So the electron in an excited state will immediately drop to a lower energy position. That means dropping down to a lower numbered or lower energy orbit, but it won't necessarily be the same one the electron came from. Like I showed with the example where an electron jumps from n equals 1 to n equals 3, it could then drop back to n equals 1, or it could drop to n equals 2 and then n equals 1. So you get a whole lot of different possible transitions going on, even in an atom like hydrogen with only one electron. Whenever the electron falls to a lower energy or lower numbered orbit, there will be an emission of electromagnetic radiation, often in the form of light, or it could be ultraviolet or infrared or X-rays or radio waves, or any kind of electromagnetic radiation would be possible, theoretically anyway. Each transition from a higher energy orbit to a lower energy orbit results in a line in an emission spectrum. And that's why you can have such a fairly complicated spectrum, even for something like hydrogen that only has one electron. The Bohr model actually can be extended to apply to anything with one electron. hydrogen normally has only one electron, but there are other things that have one electron also, like He plus, the helium plus 1 ion. Lithium plus 2 ions have only one electron. Beryllium plus 3 ions. Boron plus 4 ions, and so on. Each of those has only one electron. And those are known as hydrogen-like atoms or ions. Hydrogen-like in the sense that they have the same number of electrons as hydrogen. For hydrogen-like atoms or ions, you can use the equation, the energy of an electron in a given orbit is now equal to k times z squared over n squared. Okay. K is still 2.18 times 10 to the minus 18 joules. The addition is Z, which stands for atomic number, and also corresponds to the number of protons in the nucleus, of course. Okay, which is the same as nuclear charge. So that is the one addition compared to hydrogen. If it's not hydrogen, but it still has only one electron, then you can use an equation very similar to what we use for hydrogen, only you have to include the atomic number squared in it. If you take z squared out of this, you get the same equation we had for hydrogen. And in fact, you can use this equation for hydrogen too, because hydrogen has atomic number 1, and so that means z would be 1 for hydrogen, and 1 squared is just 1, so it doesn't affect the equation. So this equation actually works for anything with 1 electron. But anything with more than 1 electron, this equation does not work, because things just get, like I said, with 1 more electron, things get infinitely more complicated. Okay, the size or radius of the circular orbit, the radius being the distance from the center of the nucleus to the outer limit of the orbit. So say for this orbit, radius would be like that. For the third orbit, is the radius of the orbit is going to be n squared over, that is the orbit number squared, over the atomic number times a naught, or a sub 0. A sub 0 is the Bohr radius, which is 5.292 times 10 to the minus 11 meters. That's a constant. So you can find the radius of an orbit. And an example of using these equations would be referring to equation or figure 6.15. Suppose the electron is promoted from n equals 1 to n equals 6. What would the energy be in n equals 6? Well, actually, figure 6.15 is hydrogen, which means you could have used the original equation back a couple pages ago, the one without the z in it. But what we're about to see is the fact that you can use this equation for hydrogen too, because it's going to be, that equation should be negative kz squared over n squared. So the energy is going to be negative kz squared over n squared, which is minus k, which is 2.18 times 10 to the minus 18 joules, times the atomic number for hydrogen is just 1, so that's 1 squared, divided by the orbit number squared, which is going to be 6 squared in this case, and that would be minus 6.06 times 10 to the minus 20 joules. That would be the energy for that one particular electron in that one particular orbit. And of course, that's a very small energy, but electrons are really small, so you wouldn't expect them to have a lot of energy for any individual one. All right. If you wanted to find the energy of a transition, in helium plus, now, of course, if you want the energy of an electron transition for hydrogen, you can just use the Rydberg equation, this equation here, and that gives you 1 over wavelength. So whatever answer you get out of this, you can just take 1 over that, and that will be the wavelength. And then you could use E equals hc over lambda to find the energy. But if it's not hydrogen, then what you have to do is find the energy in each orbit individually and then find the difference between them. And in this case, we're looking at an electron that falls from n equals 5 to n equals 3 in a helium plus ion. Helium has an atomic number of 2. And so we use the equation for, the equation for the energy of an electron in a given orbit for hydrogen-like atoms. So the energy of the electron in n equals 5 is going to be negative kz squared over n squared, which is going to be negative 2.18 times 10 to the minus 18 joules times 2 squared, because z is 2 here, over the orbit number squared, which is 5 squared, or 25. And that turns out to be negative 3.488 times 10 to the minus 19 joules. And the energy in orbit 3 will be negative k times z squared, which is 2 squared again, over the orbit number squared, so that's 3 squared, or 9. And that works out to negative 9.69 times 10 to the minus 19 joules. Then the delta E will be E5 minus E3. So that's energy in level 5 minus the energy in level 3. And that comes out to negative 6.20 times 10 to the minus 19 joules. Regardless of the way it comes out mathematically, you can decide what the sign on delta E should be based on what's happening to the electron. In this case, the electron is falling from a higher energy higher energy orbit further from the nucleus to a lower energy orbit closer to the nucleus, which means the change in energy should be negative because energy is being released from the atom. So delta E should be negative 6.20 times 10 to the minus 19 joules. Okay, if you want, it actually asked for the delta E, so that would be the answer. If you want to know what the wavelength is, though, or the frequency for that matter, once you put that delta E into an equation, you would have to drop the sign because wavelength and frequency can only be positive. If you put a negative energy into the equation, you're going to get a negative number, and that can't happen. So if you ever get a negative wavelength or frequency, drop the sign, make it positive. Energies can be negative, but wavelength and frequency cannot. So we know the equation E equals hc over lambda. That is energy equals Planck's constant times the speed of light divided by the wavelength. Rearranging this, remember algebraically, when you're solving for something that's on the bottom of a fraction, you can just switch it with what's on the other side. And so lambda equals hc over E. So that's 6.626 times 10 to the minus 34 joules seconds for H, times 3 times 10 to the 8th meters per second for C, over E, which is 6.20 times 10 to the minus 19. Remember, drop the sign. And we get a wavelength of 3.21 times 10 to the minus 7 meters. That would be 321 nanometers, which would be in the ultraviolet range. But the question didn't ask that, so you wouldn't have to do that. Okay. Sorry. The Bohr model of the atom was much better than the previous models, but there were certain things that it didn't account for. One of them would be the interactions between the electrons and why the Rydberg equation doesn't work for anything with more than one electron. But it was a very good model, and some of the things it did account for were that the energies of electrons are quantized because they can only exist in certain distances from the nucleus, and that is in orbits. It showed us that the location of each electron is described by quantum numbers with only certain values allowed. And the only one that we've cut, the only quantum number, actually, they weren't called quantum number until quantum mechanics was developed like 20 years after Bohr's time. But we have actually already seen the first of the quantum numbers, which is the principal quantum number, or orbit number, or n. And later on, this would become known as the principal quantum number. Okay, so Bohr actually pioneered that, or at least got the ball rolling on quantum mechanics by devising the orbit numbers, which are now known as principal quantum numbers. And because, you know, the orbits were in defined locations in space, and the electrons can only exist in orbits, that accounted for the quantization of the energies that could be absorbed or released. The energy of electrons increases, or in other words, becomes less negative farther from the nucleus. So the energy goes up as the orbit number goes up. Although it's important to realize that that increase in energy as the orbit number goes up is not linear. There's, in fact, a huge gap between the first orbit and the second in terms of energy. And then between the second and third, there's a smaller gap. And between the third and fourth, there's a smaller gap. And actually, the gaps in energy get smaller and smaller and smaller the further out you go from the nucleus. Okay, so that's something to keep in mind for future reference. Separate and distinct lines in the emission spectrum result from the quantized electron energies. So Bohr explained that. So far, so good. Now, getting into the next step, which was quantum mechanics or quantum theory. And again, this was, basically physicists started looking into this because of some of the questions that still were not answered by the Bohr model. And certainly as technology improved and we were able to investigate things in more and more detail, more and more problems with the Bohr model became evident. So questions like, for instance, why are electron energies quantized? Why can electrons only exist in certain orbits? And why are those orbits at certain distances from the nucleus? Why can't there be an orbit just anywhere in an atom? Why can't you have electrons that are halfway between n equals 1 and n equals 2? Why does it have to be one or the other? So those are all questions that were not answered in the Bohr model. Why doesn't the Bohr model work for anything with more than one electron? You can actually sketch out atoms with more than one electron as if they were Bohr atoms, but the actual Bohr model and the equations that Bohr came up with don't work for anything with more than one electron. So that's when we mean the Bohr model doesn't work for anything with more than one electron. The electron or the equations don't work. And it turns out that the reason for the failures, if you will, of the Bohr model come down to differences in behavior of matter when it gets very, very small. It turns out that Newton's ideas on the behavior of matter, Newtonian mechanics, as it's called, was perfectly valid for macroscopic size objects. Things from, say, the size of a large molecule on up. So, you know, things that are our size, you know, this paper or this pen or us or cars, things like that, they do move according to Newtonian laws, which is still pretty impressive because Newton was developing his laws about 350 years ago. So not bad, but he didn't have the ability to see things or to observe things at very, very small scales. And so it was not known in Newton's time that matter at very, very, very tiny scales, like the size of atoms and smaller, behaves very differently from matter at very large scales. Basically, when you get small enough, things start getting really, really weird. And we'll get into some of the weirdness as we go on with quantum mechanics. Sorry, so on a macroscopic scale, matter behaves according to Newton's laws. And that's because on a macroscopic scale, the particle properties are much, much, much more significant than wave properties. As I mentioned the other day, though, everything has particle properties and wave properties at the same time. It's just a question of which ones are more significant. So for larger objects, say anything from the size, like I say, of a large molecule on up, the particle properties are much more significant than the wave properties. And those are the kinds of things that Newton was dealing with. And for larger objects and macroscopic objects, the positions of the particles are well defined at any given moment. You know, if you're wondering where your car is, you probably have a really good idea of where the car is, and any uncertainty in that position is probably very small compared to the size of the car itself. And so at large scales, any uncertainty in positions normally very small compared to the object itself. Velocity is also well defined at any given moment. Or at least it can be. You know, the speedometer in your car may not be terribly accurate, but you could have it calibrated so that it would be very accurate, and then you would know your speed very accurately. Any uncertainty in velocity is usually on macroscopic objects much, much, much smaller than the size of the object. And what that means is that objects have very well-defined momentum on the macroscopic scale. So larger objects have very well-defined momentum. Momentum in physics is just mass times velocity. Okay, so if we know mass very accurately and we know velocity very accurately, then we know momentum very accurately. Now, when objects become smaller, say when an object gets to about the size of an electron, you get to the point where the particle properties and the wave properties are both very significant. And you have to take them both into account. When you get smaller than an electron, like say a photon, then you get to the point where the wave properties are much, much more significant than the particle properties. And things behave very differently at that scale. So the behavior of waves often violates Newtonian behavior or Newton's theories. For one thing, particles shouldn't have interference patterns, according to Newton. By the 1920s, it was known that microscopic objects behave very differently from macroscopic objects. In other words, microscopic objects show properties that are much closer to waves. That is, very microscopic objects much closer to waves in their behavior than particles. And this was sort of the birth of the application, anyway, of wave-particle duality. A physicist named Louis de Broglie studied wave-like properties of electrons, and he actually extended wave-particle duality to larger objects. He developed the idea of what's commonly known as a matter wave. And that means, you know, like we've been saying all along, everything has particle properties and wave properties associated with it. Even macroscopic objects, when they move, they trail an energy wave behind them. And it was de Broglie who came up with an equation for actually calculating the wavelength of a matter wave. That is a wave that's associated with something that's normally considered to be matter rather than a wave. And that is known as the de Broglie wavelength. And the equation says that the de Broglie wavelength, or the wavelength of the matter wave of a macroscopic object that's in motion, is equal to h over mv. H being Planck's constant, and mv being momentum. Okay, m is mass, and remember in equations, mass needs to be in kilograms, and v is velocity. And remember, in equations, velocity needs to be in meters per second. So now you can actually determine the wavelength associated with any object in motion. And again, that's known as a de Broglie wavelength. De Broglie theorized that the quantization of energy of electrons in atoms would be explained if the electron was really, or also, in addition to being a particle, was also a circular standing wave in which only a whole number of waves would be allowed in any given orbit. Okay. There's a figure 617 on page 302 or 312 that illustrates this idea. And I'm just before calling the end of this section of the video, I'm going to show it to you because the diagram of it I tried to draw myself is really pathetic. So that is, whoops, that is the diagram I'm talking about. I'm not sure how sharp it looks here. You can look at your own copy if you want to see it in more detail. But anyway, we've got a nucleus of an atom here, and we've got what we would normally consider to be the location of the orbit given by the dotted line. And if the electron, in addition to being a particle, is also a standing wave, then what you would have would be an undulation in the wave around the atom, with one wavelength being the distance between the peak of one wave and the peak of the next. And so in this atom, you've actually got 1, 2, 3, 4, 5, 6 entire waves around the atom. And de Broglie's theory was that different orbits would allow different numbers of waves around the atom, but in each case, it would always be a whole number of waves. And that is why energy ends up being quantized in the de Broglie theory of things. Okay, so that's a little over 25 minutes, so I'm going to call it there, and we'll be back with part C in just a moment.